So this morning, actually, you're going to be learning about a new concept in this unit that we call specific heat. And specific heat is a new idea. But before we get to the new idea, we have to talk a little bit about heat, thermal energy, and temperature again. So there's a couple of things that you need to remember. You need to remember that let's see, that heat is a transfer. It's a transfer of thermal energy between objects. Make sure you write that down. You need to remember that thermal energy is the movement of particles. So make sure you write that down. And you also need to remember that temperature is the average energy, the particles in an object. So make sure you write those things down. And you might want to pause the video and you might want to, as you're writing those things down. Another thing that we should probably remember is that if two objects of the same temperature have different masses, they have different amounts of thermal energy. The more mass of the object has more particles, and as a result, will have more thermal energy. So one thing that we could probably think about is, how does this relate to your heat transfer lab? Well, in the heat transfer lab that you guys did, we had a big beaker and we had a small beaker. And I would imagine that in the big beaker, we had a lot of water compared to the small beaker, which had a little bit of water. So heat transfer was occurring from the more massive object to the smaller object. So just something to kind of relate to the lab that we just did. Now, you don't necessarily need to write this down, but I do think it's important that you might listen to it. So you've heard the phrase, it's cooler by the lake in summer. You may not have heard the phrase, it's warmer by the lake in winter, but it actually is true. Now, let me try to explain why it's cooler by the lake, Lake Michigan, that is, in the summer. So what happens is that the lake tends to draw in heat from the surroundings. So as the sun beats down all summer long on the lake, and it beats down on the city, and it beats down on the environment, the ground and whatever else, the lake is this giant suck of heat energy, and it actually absorbs that heat. You might notice, if you've ever been to Lake Michigan, like in June, it's freezing. And if you go to Lake Michigan in August, it's still cold, but it's less cold than it was in June, because it takes like 2.5, 3 months for the lake to actually warm up. Now in the wintertime, all of that energy that the lake had absorbed all summer long, it starts to slowly release that energy back into the environment and warming them up slightly. So a lot of times, if you're ever watching the news in the morning, and it talks about temperatures in the wintertime, the temperatures near the lake are oftentimes a little bit colder than the temperatures away from the lake. Water is one of those objects that is special, and it resists temperature change. In science, we say that water has a very, very high specific heat, which is something we're going to talk about today. So, what is specific heat? I keep talking about it. Here's a definition. You might want to copy it down. So specific heat is the amount of energy that is required, the amount of heat rather, that is required to increase the temperature of 1 kilogram of a substance by 1 degree Celsius or Kelvin, but we'll probably stay in the Celsius area. So what really is it's a measure, or it's a value that we use in science to sort of allow us to calculate heat change. Now, there are some materials like metal, think about copper or a spoon, that have incredibly low specific heat. And as a result of that, they increase their temperature really quickly. And then there are other materials like water that have a really high specific heat, which means that it takes a lot of energy to increase their temperature. So they increase slowly. Okay. So specific heat is defined one more time as the amount of heat required to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. So here are some things that you probably are going to want to write down. First of all, the word formula, or the word equation for specific heat is equal to mass times the value for specific heat times change in temperature. This formula right here is the way that we represent that on paper. Q, for some reason, I have no idea, it just is is the variable that we use for heat. So anytime you see the letter capital Q, that means we're talking about heat. And capital Q, or heat, is always in joules. M is mass, and those have to be in kilograms. Specific heat is this is lowercase c, and that is joules per kilogram per degree Celsius, which is written over here as the label joules over kilogram times degree Celsius. You might want to like put parentheses around this to remember that that's actually all of that is being on the bottom of the fraction. And then change in temperature. We've seen this triangle before. That triangle tells us that the temperature has changed. Temperature will always be in degrees Celsius. And so those are the variables that we're going to be using. So you might want to pause the video and write these things down, and then we will go through a couple of practice problems before you get your homework. So here's the first practice problem. The practice problem says the specific heat of glass is 753 joules per kilogram degrees Celsius. If the temperature of a glass sample increases by 10 degrees Celsius when 2,450 joules of heat are applied, what is the mass of the sample? Well, I want to use the formula. Q is equal to mass times specific heat times, oops, I don't like that, times change in temperature. So the first thing I'm going to do is I'm going to go ahead and I'm going to identify my variables. Q, M, C, change in temperature. Now, this problem has me identifying, it tells me a couple of things. First of all, it says that the specific heat of the glass is 753 joules per kilogram degrees Celsius. So I'm going to plug that in right here. 753 joules per kilogram times degrees Celsius. And then I know that, and then it says that the temperature of the glass sample has increased by 10 degrees Celsius. So the change in temperature is 10 degrees Celsius. I'm also told that 2,450 joules of heat are applied. So I know that Q, which is heat, I know still is silly, 2,450 joules. So what I'm going to be solving for in this problem is, again, I'm going to be solving for the mass. Okay, so I'm going to start filling in my variables. So over underneath my formula, I'm going to take 2,450 joules equals mass times the specific heat, which is 753 joules per, oh, that should be kilogram over here, kilogram degrees Celsius times the change in temperature. And the change in temperature we found according to the problem was 10 degrees Celsius. So the first thing that I'm going to do is I'm going to go ahead and I'm going to combine what I can. So I'm going to multiply 753 times 10. When I do that, I get 7,530. So I'm going to rewrite what I have. So I'm going to take the 2,450 joules equals mass times 753 times 10 degrees Celsius would be 7,530 joules. Okay, now check this out. Degrees Celsius over here is over 1, so it cancels out. So it's just joules over kilograms. And I did not write that very well, so I need to go ahead and fix this a little bit. Erase some of these things here because it should be 7,530. I'm sorry. So it should be 7,530 joules. Now, at this point, I have to solve for the mass. So in order for me to solve for the mass, I'm going to have to divide both sides by 7,530. So 2,450 joules will equal mass times 7,530 joules over kilogram. And I'm going to divide both sides by the 7,530. 7,530 joules over kilogram and 7,530 joules over kilogram. And on the right-hand side, that cancels out and it leaves me with just M. So when I plug 2,450 in the calculator and divide it by 7,530, I get a value of 0.32 kilograms. So the mass of this particular piece of glass was 0.32 kilograms. So that's how we go ahead and calculate the mass. It's not too bad. We're just plugging things into our formula. The next one that we need to do is a little bit more complicated, so I'm going to take some time to go through this one a little bit. It is a mug of hot chocolate giving off 17,500 joules of heat into the air around as it cools. So we have hot chocolate. If the hot chocolate has a mass of 0.2 kilograms and its final temperature is 32 degrees Celsius, what is its initial temperature? So in this case, we have to figure out what the initial temperature is. So once we take the hot chocolate out of the microwave or off the stove or whatever, and we pour it in the mug, we throw a thermometer in there and we figure out that what its initial temperature is. We can calculate that without actually doing that, like using a thermometer. So we have Q, we have M, we have M should, hang on. I got this. Oh, no. That's silly. Just erase all that. Okay. So Q, mass, specific heat, which is C, and then change in temperature. Okay. So let's read through the problem. It says the mug of hot chocolate gives off 17,500 joules. So I have 17,500 joules of energy. If the hot chocolate has a mass of 0.2 kilograms, 0.2 kilograms, and its final temperature. So now here's how we're going to handle this. We don't know what its change in temperature is, so we're actually going to end up solving for change in temperature. We know its final temperature, and we'll need that later, so we'll hang on to that. We get to assume that the specific heat is of the hot chocolate is 3,930 joules per kilogram degrees Celsius. All right, so let's set our problem up, or our formula up rather. So we have Q equals M times C times delta T. Okay, now, so I'm going to plug in what I know. So I know that Q is equal to 1,750, or 500 rather, 17,500 joules. I know that the mass is 0.2 kilograms. I know that the specific heat is 3,930 joules over kilograms degrees Celsius. and I know that we're solving for delta t. That should be a better triangle than that. Okay. Now, I am going to first of all take 0.2 and I am going to multiply it times 3,900. So 0.2 times 3,930 gives me a value of 786. So when I go to start filling in my values, or simplifying this problem, I have 1,500 joules equals 786. Now here I see that kilograms cancels out, so my unit is actually going to be joules over degrees Celsius times delta T. Okay, so now what I need to do is I need to get delta T by itself, so I'm going to divide both sides by 786. So I'm going to rewrite the problem. 17,500 joules equals 786 joules over degrees Celsius times delta T. Well, I'm going to divide both sides by 786. Joules degrees Celsius, 786 joules degrees Celsius. And on the right-hand side, that cancels out, and I'm left with delta T. Okay, so 1,700, man, geez, 17,500 divided by 786 gives me a value of 22.3. So my temperature here is going to be 22.3 degrees Celsius. So see how joules cancel out over here? Now, that would be great if we were solving for change in temperature, but the problem is asking us to identify the initial temperature. We knew the final temperature was 32 degrees Celsius, so we have to go back and think about what delta T means. Okay, so delta T means TF, T final, minus T initial. Well, I'm going to rearrange the formula so that we're just solving for the initial temperature. And when I do that, I get a value of, or not a value, but I get a formula of Ti equals TF plus delta T. Okay, so for Ti, I find out that the final temperature from the problem was 32. What is that? Was 32 degrees Celsius, and the change in temperature was 22.3 degrees Celsius. So in this problem, I know that I'm going to add these things up. So to get my initial temperature, Ti, 32 plus 22.3 is 54.3 degrees Celsius. So the actual answer to this problem is 54.3 degrees Celsius. That was the temperature at which we took we got the hot chocolate. Okay, so you're going to go ahead and have to complete, I believe it's worksheet number 4. It is specific heat part 1 calculations, and that will be your homework. You can work on that in class, and then what you don't finish will be due for Monday. So we'll go from there. We gotta stop this. How's it going?